So, if you don't have any questions for those, then what was our memory trick for the 30, 60, 90? We don't even have to write this down. I just want to see if we can remember which one gets which. What two multipliers does the 30, 60, 90 use if referencing the short leg? And you can check your handout. 2 and the square root of 3. Which of those values is larger? 2. So, does the 2 go to your hypotenuse or your leg? The hypotenuse, right? So that's the biggest thing to remember with your 30, 60, 90 is it uses 2 and radical 3. The 2 is larger. And that's if we're referencing the short leg. I also gave you guys on the handout, you don't have to get it out, but do you still have your handout from last time? Yeah. Because I have extras, is what I was offering. If you reference the hypotenuse, then it was a little bit weirder, and we had this table that when we reference the hypotenuse, we really have half the hypotenuse and radical 3 over 2 times the hypotenuse. Hey, what's up? I am. Why? Yeah, let me call you back in 40 minutes. All right, love you. So then 45, 45 was easy. What's the multiplier in 45, 45, 90? Square root 2. Yeah, so radical 2 instead. And I remember that because the two angles that are identical and or the 90 is double the 45. Like everything is kind of 2 here. There's two similar angles. This is double. Yeah. So now let's talk about the names of the sides. Do you guys remember why hypotenuse is called hypotenuse? Do you remember from stems, and this maybe didn't happen, but do you remember from stems what hypo means? If you are hypothermic, is your body temperature warmer or lower than it should be? It's lower. Hypo means beneath. So actually, why hypotenuse is called hypotenuse is it's beneath or under. Hypo actually means under. So hypothermic means under temperature, right? Your body's under the temperature it should be. The hypotenuse is under the right angle. But then we start talking about sides that are opposite and adjacent. So what I want you to do is head your paper with trig ratios. Or you can write out the whole word trigonometric if you really want. You what? Okay, so I'm teaching until the middle of second AO. So if you're still available second AO, come back and talk with me then. Otherwise, catch me at extensions. All right, thank you very much. They should know better than to send me kids in the middle of my class. All right, date as always. All right, so draw a right triangle on your paper. We know that the hypotenuse is across from the right angle. But, and here's why I didn't even want to put this on a handout for you guys. I want you to draw it so like you're more familiar with it. We need to ask ourselves to figure out opposite and adjacent. What is the angle that we are referencing? So, if we decide that we're going to label these angles A, B, and C. So go ahead and on your paper label A, B, and C. Hypotenuse is always the hypotenuse. But opposite and adjacent can actually be either or. And this is where it's complicated. Because if you're like, so wait, you're telling me the short leg could be the opposite or the adjacent? Yes. The long leg could be the opposite or the adjacent? Yes. It depends on what we use as our theta. So theta, you guys heard about theta before? Have we talked about theta? Theta is this. Let's go ahead and write down the word theta. Theta looks like an Easter egg. It's like a circle with a squiggly across the middle. And sometimes it doesn't even look like a squiggly. Theta is what we use to talk about an angle. And how big it is. So it's the angle measure. So if A is our theta that we're looking at, so we'll say A is our theta. And don't ask me if there's an exact right way to draw theta, because there's like a few. Because remember, theta is a Greek letter. So really, it's probably like an O with a line across the middle, and then over time has kind of changed a little bit. If A is our reference angle, then our opposite is opposite the angle. So if A is theta, then BC is opposite. And what that also means is CA is adjacent. Because we know the word adjacent, and if you need to write this down, adjacent means next to and touching. So remember, it doesn't just mean next to. It means next to and touching. My neighbor beside me is an adjacent property. But my neighbor across the street is not adjacent. They're across the street. We're not touching. There's a street between us. But my next door neighbor, he's adjacent to me. What's up?
Are we going to get any more Khan assignments?
I don't know, but I'm teaching right now. Talk to me later. I mean, yes, there's always more Khan Academy. That's the short answer. So here's the tricky part, though. And I'm going to change colors, and if you don't change colors, I would not write this down. If B was our theta, our opposite would now be the AC. And our adjacent would be the BC. Right, so you have to look at what is the reference angle being used to determine what's the opposite and the adjacent. If you don't know what angle you're talking about, you can name the sides whatever you want. But then it determines what angle you're talking about. We cannot talk about both acute angles at the same time. So we've got to pick one of them. Why can't we talk about both acute angles at the same time? Because trig ratios. So, here. So this is essentially like what we did last time. But if we, I'm debating if we need to set this up. Probably not. If we just look at this, right, I'll go ahead and say you probably don't need to draw this. And maybe I'll give this to you guys on a handout and the next time we come to class. Thanks, gravity. So what do we know about similar right triangles? And this kind of goes back to CPCTC. Like congruent parts of congruent triangles are congruent. But what about like similar parts? Like if we know that our small triangle is a 6, 8, 10. Oh wait, 6, 8, 10. What's 6, 8, 10 remind us of? 3, 4, 5. So what we can think back to is, oh yeah, well, we actually had another triangle that had 3, 4, and 5. Or no, sorry, 3, 4, 5 this way. I'm reading my table backwards. Right? Yeah, 6, 8, 10. So, when we actually take a protractor and do the measurement, what is interesting here is angle A is a perfect 37 degrees. And we could flip that statement around and say if we make a perfect 37 degree ramp, that is of length 5. Its legs will be 3 and 4. If you make that same ramp bigger, what happens to the lengths? They will scale proportionally, right? So what we're going to find is this proportional relationship here between this scaling of, okay, if this became 9, you guys, I know this feels a bit elementary right now, but if this became 9, what would this become? 12, and then 15. Okay, if this became 12 as we scale up the triangle, okay, so times 4, this would be 20. If this became 15, times 5, okay, so this would be, oh, this one is also 20, because this then is the other leg. So we then actually flip this thing around and start to say, well, okay, also in right triangles, if I know one of the acute angles, you guys got to wait until second AO. Sorry, I have class until then. Can you remind the other teachers that I'm teaching right now, like whoever sent you here? The last angle, when we know two angles, we know the last angle. What would the last angle be here? Do some quick math, right? 90 minus 37. Oh, guys! 53, right? Take away the 30, then take away the 7. Take away the 30, then take away the 7. So, I have to clear this while I'm up here. We're working towards this really great moment. And that really great moment we're working towards is having our calculator do everything for us. Because someone smarter than us said, hey, if this is always true, and every right triangle with an acute base angle of 37 degrees will keep these ratios, then I can standardize that ratio, right? So we start to actually standardize these ratios for certain degree measures. So if we look at the ratio of 6 to 8, or 10 to 8, or 10 to 6, or I think I got all of them. We can standardize that ratio, right? We'd have 0.6, 0.8, 0.75, right? 6 to 8. We can compare our leg lengths, and we know the ratio that will preserve the whole time, no matter what size of triangle. So in Khan Academy, one of the first things that we need to do, give it to me actually. If you didn't turn it in on time, I need it now because all of those are graded. Thank you very much. I'll give it back to you later, bud. So, if we know that our leg lengths, and sorry, the other one's kind of hard to see. This is 3.2 and 11.9. What is the ratio created between the legs? Oh, wait, we have to check what are the legs we're dealing with. So, with L as our reference angle, what leg are we dealing with? Hypotenuse or adjacent or opposite? What legs are we dealing with? With L as the reference angle, well, are we using the hypotenuse? No, right? We're not using the hypotenuse because the hypotenuse is across from the right angle. So we're using opposite adjacent. So we need to come over here and say, okay, what really smart mathematician who solved these things, like what row of this has opposite adjacent? Okay, the bottom row. So now we're looking for, with the opposite and adjacent, put the opposite over the adjacent. So grab a calculator and do 11.9 divided by 3.2. Or if you in your head can approximate it well enough, since we only have 3 options here, how does approximately 12 compare to approximately 3? Yeah, approximately 4, right? Thank you. I was also hoping you guys hadn't just both lost your voices. So, what is this angle approximately going to be? 75. Now, if it works out exactly, then it's exactly. But right now, we're approximating. So as you go through your Khan Academy homework that looks like this, we really are just saying, so approximately match these things. right? Oh, that's the only one of those that I gave as examples? Okay. Does that make sense? That all you're going to do is literally look for which one am I given, and you're given this table in each question there on Con. So look for what legs do I have, or hypotenuse, what edges, sorry, I should start using that word. What edges do I have? What does the division come out to be? And then that will tell us the angle. Now what's sweet is, again, that person who's smarter than us put all this into the calculator for us. And not only did they put it into the calculator for the nice angles of 55, 65, 75, they put it in for every stinking angle. So the reason we pay so much for these handy-dandy calculators that we probably don't really need these days because the internet is it is programmed with all of it. So when we then, I think this is the next Khan Academy assignment, we're still working towards using the calculator to do all of our hard work. When we now look here, it says use one of the triangles to approximate MO in the triangle below. So am I going to use triangle 1, 2, or 3 over here? Yeah, I'm about to have to start calling on Calvin. 2, right? Because it has the 35-degree angle. So now in your head, match things up. Okay, so the reference triangle we have so that the hypotenuse can be 10. Guys, this is actually the unit circle. This is actually 1. So this is actually 0.57 and 0.82. And we'll circle, see what I did there? We'll circle back to all this later, but I want you to have this filter of like, wait, this is all actually from the unit circle. So just remember that. So the short leg is 0.57 of the hypotenuse, or 5.7 compared to 10, right? The long leg is 8.2 compared to the hypotenuse of 10. If we use the unit circle type solving for this, which I'm going to, they ask us MO. Is MO going to be the short leg or the long leg? And how do we know? Calvin, now you got to answer because you've been quiet for too long. Is MO going to be short or long, and how do we know?
Should be the long.
Yeah, why? How? Yeah, I'll let that maybe slide. What I really would have made my week if you said hinge theorem, which we've talked about, but only really briefly. Remember, hinge theorem says across from the bigger angle will be the bigger opening. So the door with the bigger angle opens the bigger distance, right? So a 35-degree angle of opening versus, well, this has to be more than 35, right? So hinge theorem tells us, well, if this is the larger angle, MO is the larger side. So I'm going to write down the comparison of the long leg to the hypotenuse, which if we did unit circle would be 0.82 to 1. And that would be proportional to something related to 8. The reason I like to take these things back to the unit circle and the hypotenuse of 1 is then I find the math to be easier. Now we could always cross multiply and divide to solve. Excuse me, but I think a straight up multiplication by 8 isn't too bad. What do we get here? 6.57. 6.56. Any questions on using a reference triangle? Solve this one on your own. we first have to ask, what is WY over WX? What's that going to be, Ellie? Is it short to long, short to hypotenuse? What is WX? It's short to hypotenuse. So I, sometimes in my notes, just to keep things straight, will write short to hypotenuse. Like, because I use S, L, and H, right? Short, long, and hypotenuse. So what we're comparing is short to hypotenuse. In a 70-degree triangle, okay, well, in the 70-degree triangle, short to hypotenuse is either 3.4 over 10 or 0.34 over 1, or I could do any manipulation of that I want. But in the 70-degree triangle, 20, 70, 90, if you want to say, we have these consistent ratios of 3.44 and 10. Really, it's 0.34, 0.4, and 1, but we scaled it up to make some better numbers. Now, what would be even better be 34, 40, and 100, right? If we wanted to scale these up to integer triangles. So, like, we could. If you don't like using 1 and decimal values, you could make your hypotenuse 100. And then you'd have 34, 40, 64, 77, 82, 50, right? It'd make everything whole numbers. That'd be kind of nice. So here, 0.34 would be our answer. With these questions, the trick that you want to make sure you're paying attention to is what is the comparison? Check what this ratio is, short to long, long to hypotenuse, short to long, whatever. So, do we have any questions on the reference angle determining the name of the sides, whether it's opposite or adjacent or hypotenuse? Well, hypotenuse is always hypotenuse. All right, so now for the meat that everyone has been waiting for. It's like the main course of trigonometry. SOHCAHTOA, right? Which is probably what anybody who says, like, hey, have you heard about trig? And you're like, yeah, that SOHCAHTOA thing? And that's what I hate. Because that means people don't know trig. They know a memory trick. So on your paper, if you would write down, and I hate this, but somewhere, and I'm just going to jot it here because I have space, big S. Well, actually, so this is what a lot of people write it like. SOHCAHTOA. Or they write it in all caps, which I also think is wrong. How I would like you to visualize it So you can remember SOHCAHTOA. That's fine. But what the heck does SOHCAHTOA mean? It's just a memory trick. Because what it's actually telling us is if working with the sine function, the sine ratio of a referenced angle, the thing that spits out of your calculator, the column it goes to in a table, literally it's got a table programmed into the calculator, it will spit out the ratio of the opposite side over the hypotenuse side. So if you plug in 20 degrees or 30 degrees or 40 degrees or whatever degrees, that is not 90. Because we can't use the right angle as our reference angle. We'll dig more into that later because I don't have much time today. Likewise, ka, but people like this only makes sense if you can remember how to spell it correctly also. Ka is not just how they say car up in the Midwest, or like, up in like Maine and those areas. Ka means the cosine function in your calculator when you plug in a reference angle, spits out the ratio adjacent over hypotenuse. And you can probably make a pretty good guess about tangent. Tangent of your reference angle equals the opposite over the adjacent. Now, what did we say is dangerous when we go to start doing trig in our calculators? What do we have to double check that is set correctly? Radians or degrees in our mode menu. So everyone go to your calculator mode menu before we go any further and check that we are in degrees. Everything else is pretty fine. Like, I don't know, we can fix things if things come out wrong. Scientific versus normal, we just normally have it on normal. Math print versus classic, that'll determine on if you get like decimal answers or radical answers. It spits out your answer in radical form. I like math print better because it spits out in radical form. This is for whether we do real or imaginary number representation. So just because I don't know if we've ever really talked about the modes in here too much, if you want it to spit out imaginary solutions, you switch it to being able to spit out imaginary solutions. And then instead of giving you an error on like square root of a negative, it'll give you an answer, which is pretty cool. So if you want to play with these other settings, do that some other time. But as long as we have that fixed, let's dive into like, wait, what do you mean I can just use my calculator to do all the work? So the sine of B, which, guys, this is actually another Greek symbol, and I'm just using B because forget them bringing in other Greek symbols. Or I forget, this might be lowercase theta, but I don't think so. I think that's beta. Either way, it doesn't actually matter what Greek symbol we use. They're all interchangeable. So for these three triangles, what's the sine of B? Well, guys, actually, we don't need our calculator. What I just showed you in your calculator is for when we know the angle and we're trying to find the sides, or a side. Sine, according to our notes, sets up the ratio of opposite over hypotenuse. Okay, so for this first triangle, the sine of B we would write in that triangle, whatever the size of that, sorry you couldn't see that, sine of B, B is like our input, right, because sine is a function. That function just corresponds to a table of ratios, right? But if the sine is always opposite over hypotenuse, well, from B, which side is the opposite? 4, right? Because the 3 is adjacent. So it would be 4 over 5, which is actually 0.8. Your calculator can then say, 0.8. I remember 0.8. There was this other triangle that had a ratio of 0.8. Right? Like, now, not that it is necessarily one of these triangles, but literally, like, your calculator just has every possible triangle in its database. And it says, what angle matches with the ratio of 0.8? And it gives it to you. So instead of us having to go match it with a table, we just let our calculator do that matching for us. So likewise, in the second triangle there, what is the sine of our B? I'm just trying to get you guys used to looking at opposite and hypotenuse. So we don't even have to write these down, guys. Sine of B here, 15 over 17, right? Sine of B here, 12 over 13. What we should notice is since the hypotenuse is always the longest side, what do we notice about every ratio that we get for sine? If the hypotenuse is in the denominator, and it's always the longest side, these ratios are always going to be less than 1. So if you try in your calculator, and I'm going to show you how to do what I'm about to do in a second, to type in 5 over 4 instead of 4 over 5, don't try to do what I'm doing because I did not just hit sine. Doesn't work. It knows something's wrong. And it takes you to it and it says, yeah, what you typed in here can't work. So 4 over 5 could, and that angle is 53.13. Why do I have that little 1 up there? Because I'm not using sine. I'm using the inverse function of sine. Remember, the power of a -1 is the inverse of a value. So, I got time. I got 10 minutes. We're going to get to it. Don't you worry. Cosine of those 3 triangles. Same 3 triangles. Let's at least write down the first one. So, cosine of that triangle. The cosine, though, is always the adjacent over the hypotenuse. What's the adjacent side to be in our first triangle here? Oh, well, yeah, in the middle triangle, yeah, it'd be 8. Over here it'd be 3, and over here it'd be 5, right? So the adjacent side over the hypotenuse, so like in this case, it would be 3 over 5. Here's the cool thing about trig. I can choose whether I use sine or cosine, and I'm going to get the same answer either way. I just have to make sure that I switch what I plug in. Opposite over hypotenuse, adjacent over hypotenuse. Either way, I was referencing the same angle, right? If you look, I set this up so that these 3 triangles are the same on all 3 of these slides. The only thing changing up here is sine, cosine, and tangent, right? So if we use the same reference angle and the other function, well, wait, so tangent is opposite over adjacent, right? Opposite over adjacent. Same answer. So sine, cosine, and tangent are all interchangeable. The thing that determines which one we choose, what 2 sides do we know? Or what side do we know and what side are we trying to figure out? So let's look at what in the world I mean. If we were given a 40-degree angle and a hypotenuse of 7, please copy this triangle real fast. Doesn't need to be pretty. Let's, on our paper, to get a bit more comfortable with this, label that if the 40-degree angle is what we're working with. Now I say if, because guys, can we figure out the other angle? Yeah, we could figure out this other angle real easy. But if we work with the 40-degree angle, then this side, my question mark side, is actually the what? Opposite or adjacent? Opposite. From the 40, it's the opposite. So that's the opposite. And the other side that I have is what? It's the hypotenuse, right? So, which trig function uses opposite and hypotenuse? Go back and check your SOHCAHTOA, right? Opposite and hypotenuse is used by sine. So here's what we're going to set up. sine of 40 is equal to that opposite side, we don't know it, over the hypotenuse. Now, we could, in our calculator, say, okay, calculator, tell me what the sine of 40 is. And then we could say, all right, well, this is equal to 0.642, and we can solve it from there. Or, guys, let's be algebraic here. How could we isolate this value? Multiply everything by 7. So when we want to isolate the opposite, right, we'll call this x, we can just multiply by 7. And like literally the whole thing is multiplying by 7, so this wipes out. We're going to say x is equal to 7 times the sine of 40, which literally you can just type into your calculator the number 7, the button sign, and the number 40, and you don't even have to close your parentheses if there's nothing else after it. It assumes a closed parenthesis, and it tells us our other side is 4.49, but if we're rounding to the nearest hundredth, that would actually round up to 4.5, because 4.50 technically. I don't even want to ask yet, does this make sense? Because I want you to try it and see if you can figure out how to make it make sense on your own. So with this one, try it on your own. You don't necessarily have to draw the triangle in your notes, but it might help. If your calculator is not set in degrees, you will get some funky answers. We are given the hypotenuse. What side are we trying to find? Opposite or adjacent? Opposite, yeah, right? So, to use hypotenuse and find opposite, we again are going to use sine. There's a trend here because he's trying to make sure that you understand it before we move on to a different function. Now here's what's cool. When they give you the hypotenuse and you start to get used to when they give you the hypotenuse, since the hypotenuse is always in the denominator, it's always the thing that we can multiply by to solve, right? So I again here can just do 5 times the sine of 45 to get our answer. So do that. .53? 3.54 if we round to the hundredth. Be careful, because Con tells you round to the hundredth. Why are you giving me a weird look like you're guilty of something?
I think
You're right, because I wrote down 45. Good catch. You're absolutely right. So 5 sine 35, what'd you get? Yeah, 2.87. Let's find one that's not sine. Let's do this one. Sorry, I should not have said let's find one that's not sine because that's unnecessary. This one is different still. And I got to get you out of here in like 2 minutes, so this will be the last one that we do. I want you to try to solve it and be able to tell me why this one is different. Why is this one different? Did they give us the hypotenuse here? No. So we don't have our denominator here. So to cross multiply and solve this, and here's the trick that I want you guys to get into. This would cross multiply, this would cross multiply, then we would divide to get the h by itself. Guys, what actually happens? The h and the sine of 20 swap places. What actually happens here is the h and the sine of 20 swap places because this is over a 1. So this will become 3 divided by the sine of 20. Literally, you just swap places, and h would be 8.77. So when the denominator is the thing we're trying to find, we can actually just swap it around. And with that, I'm totally out of time. Now you guys can probably fill in the blanks of when do we use inverse function of sine is when we don't know the angle, right? So to just give you one more thing to leave on, if you didn't know the angle, but you did know both of these values, you can isolate the value of the angle by just using the inverse sine and wipe out the sine, right? So if you apply inverse sine to both sides, that's how you solve your angle. Khan's got a really good video of that if you would like to see it so that you can solve more of your practice work. I will not see you guys again until next week. But what that does mean is when Green leads on Friday, like when I teach their class on Friday, you could go watch that YouTube video if you really want to, like do homework over the weekend. Otherwise, just wait till Monday. I'll see you guys then. It's all right. Have a great day, guys. Thank you. Goodbye.